Hello, and welcome to the Academy of Useless Ideas. You might remember Pythagoras as the stern mathematician who unveiled the truths of right triangles, but did you know that he was also a cult leader and a murderer? Indeed, Pythagoras founded a religious cult based on the belief that numbers explained the true nature of the universe. Furthermore, they believed that everything in the universe could be expressed as natural numbers or as the ratio between two natural numbers. During a boat trip, one of Pythagoras' students announced that the hypotenuse of an isosceles right triangle with legs of length 1 couldn't be expressed as a rational number. According to legend, Pythagoras was so upset with the statement that he tipped his student over the side, drowning him. Whether the story is apocryphal or not, we don't care too much because in the Academy of Useless Ideas, we never let the truth get in the way of a good story. Using Pythagoras' theorem, one can check that an isosceles right triangle with legs of length 1 has a hypotenuse of length square root of 2. Therefore, what Pythagoras' student proved was that the square root of 2 cannot be written as the ratio of two natural numbers. As it turns out, the Pythagoreans were wildly wrong. There are many distances in the real line that cannot be expressed as rational numbers. The existence of these quote-unquote holes in the rational numbers will impede the study and development of limits. To illustrate that point, consider a positive rational number q0 such that q0 squared is smaller than 2. It is not hard to verify that the number q1 equal to 2, q0 plus 2 divided by q0 plus 2 is a rational number larger than q0, but such that q1 squared is still smaller than 2. Similarly, for the rational number q1, we can assign a larger rational number q2 whose square is smaller than 2. Repeating that process, we can create an increasing sequence of rational numbers q0, q1, q2, and so forth. Each new number in the sequence gets closer and closer to square root 2. Indeed, the sequence quote-unquote wants to converge to a square root of 2. However, it cannot, because the square root of 2 is not a rational number. This discussion motivates a construction of the real numbers as an extension of the rational numbers in which sequences that want to converge actually converge. Note that this method of constructing the real numbers is similar in spirit of how the rational numbers can be constructed from the integers. In the integers, every number except 0 wants to have a multiplicative inverse. Thus, we built the rationals from the integers in such a way that we would get that extra property. In analysis, the type of sequences that want to converge are called Cauchy sequences, and we will have much more to say about them later. Although constructing the reals by adding the converging points of every Cauchy sequence is valid, we will explore a different method. As a motivation, consider both the set A of all positive rational numbers with a square smaller than 2 and the set B of all positive rational numbers with a square larger than 2. Note that every element in B is an upper bound to every element in A, and that every element in A is a lower bound to every element in B. Looking at those sets, what is the largest element of A? What is the smallest element of B? Note that for every element Q in A, we can find a larger element that is also in A. Therefore, A does not have a maximum. Perhaps the requirement that the largest element should be an element of A is too strong. What if instead we take the least of the upper bounds of A? However, note that the set of upper bounds of A is precisely B, and that B doesn't have a smallest element because for every element Q in B, the element 2Q plus 2 over Q plus 2 is smaller than Q, but it is also in B. This example shows that there are bounded non-empty sets of rational numbers that don't have a least upper bound. These type of sets exist because of the holes in the rational numbers. This motivates a second possible construction of the real numbers. The real numbers can be obtained from the rational numbers by making sure that every non-empty upper bounded set has a least upper bound. This construction of the real numbers is based on the so-called Dedekind cuts. For now, we will skip the construction and instead we will accept the following important theorem. There exists an extension of the rational numbers in which every upper bounded non-empty set has a least upper bound.